Okay, welcome everyone. Glad you could come out. I'm delighted to be able to introduce Professor Todd Zickler today, who'll be our speaker. Actually, Professor Zickler is from Canada. He's originally from Vancouver. He did his undergrad in McGill, so we have a Canadian connection. And he's now a professor at Harvard University, where he directs the Harvard Computer Vision Laboratory. And Professor Zickler is really a pillar of I'd say, the computer vision and computational imaging communities. We're really glad to have him here. His research is on bio-inspired vision, using properties of light to infer things about scenes, the world around us. And I think today is going to be speaking a little bit on image representations and image processing. So if you could join me in please extending a warm welcome to Professor Zickler.
Thank you. Thank you very much. All right, it's a real pleasure to be here. I really love these kinds of events, so I really appreciate the invitation, and it's nice to see some old friends and to meet some new ones. All right, so the work I'm going to talk about is really the work of two students who I've had the pleasure of working with. So the first is Dor Verben, who's now a research scientist at Google, and the second one is Mia Polanski, who's a PhD student with me still. And the work that she did was actually while she was a student researcher at Google, and is sort of continuing since then. All right, so to sort of give you some context of saying a little bit more of what David was saying is the work that we do in our group. I sort of grew up in computer vision, being sort of in awe of biological vision systems. And one of the reasons I get up every day is not just trying to make artificial vision systems, but also trying to figure out the magic behind biological vision systems. And I think of biological vision systems like on the left there, not just as like sort of human scale, like 2 pan tilt varifocal cameras at whatever 60 frames a second, 3 colors, foveated spatial resolution, and so on. But the variety of biological vision systems that we see with different evolutionary results that sort of represent sort of co-optimizations of what measurements of light you actually collect, and the neural wiring that processes those things so that you do whatever tasks you need to do as metabolically efficiently as possible in whatever environments you happen to exist in. And so on the, sort of with that kind of inspiration, I think about the future applications of vision systems that enable autonomy, augmented reality, and I tend to be motivated by things that would like operate with sort of processing that happens at the edge, right? So rather than sort of big central cloud processing systems and a lot of communication going back and forth to some centralized engine, I'm kind of motivated like on the biology side of things that are like efficient, and they're good at doing what they have to do, and they do it efficiently. And as small and as low power as they can do it. Okay, so now within that kind of context, I sort of work on I think of it as two different categories of things in our group. One is sort of on the computational imaging side, where we're trying to co-design algorithms and optics to kind of mimicking, let's say, evolution, where you have sort of optical configurations and neural wiring co-evolving. And I went back and forth about what talk to give here, but I'm not giving this one. That's why I'm putting it here. But the one sales pitch that I wanted to make is one of the students in our group wrote this really nice optimization platform. It's basically like a framework that plugs right into PyTorch for doing co-optimization of flat optics and algorithms. And so if you want to, let's say you want to design a sensor where you have some diffractive optic or a meta lens optic with a sensor and then some processing, and you want it to produce some kind of output, and you want to co-optimize everything, then using D-flat, you can just basically have your optical layers like the first layer that you just back propagate through like anything else. And it's trying to make that as sort of seamless as possible, so that all the kind of progress that we've seen on the pure neural network side, we might be able to see on the computational imaging side too, where we can all start co-designing things and sharing designs and have it all be a little bit, have discovery accelerated a little bit. All right, so the other kind of half of my group kind of works on what I think is like sort of, large mammal primate kind of human sort of vision. And I tend to, as David said, I just naturally tend towards kind of lower level or mid-level scene understanding. So shapes of objects, materials of objects, not so much semantic understanding, like what things that I can attach, like nouns and verbs and adjectives to. And we tend to sort of think about algorithms that actually can provide the functionality that we want in practice, but then also, whenever we can, sort of try to analyze things to try to sort of see if we can characterize analytically or statistically, like when things are going to work and when they're not going to work, and exactly what the ambiguities are. And so what I'm showing here on the bottom row, for example, is a new texture ambiguity, shape from texture ambiguity that Dor happened to discover kind of by accident, where you can 3D print those two shapes on the right, and when you look at it on the left, they actually give you exactly the same thing. Okay, so that's sort of the context. So what I'm actually going to talk about today is this problem, right? And whenever you take a computer vision class, you see an image like this, and you spend some time talking about segmentation and edge detection and boundary finding, and then you pretty much every computer vision textbook there's like a catalog of segmentation algorithms, and the instructor says something like, okay, there's a whole bunch of segmentation algorithms. I'm going to show you these three. And there's no sort of rhyme or reason of which one's better or why, so, and we're still not satisfied with the ones we have. It's like this messy thing. So talking about it again is a little bit risky, but I'm kind of embracing that risk. Here we go. Okay, so the other thing that you'll sort of see in your computer vision class is this, the segmentation problem or grouping problem. Kind of, you can think about it from two directions. So one is kind of like a top-down direction, right? Like you sort of have some layout of the scene. It's a grassy field. Maybe I know where the ground plane is. I know there's kind of two zebras there, right? And just from that language description, I could draw a picture that had some boundaries and groups in it, and it might not be too far off of what's actually there, right? So that kind of top-down semantic layout is a very important cue for deciding where things are and where the boundaries are. But then there's the sort of the bottom-up stuff where you just say, look, like patches that look like they're the same stuff, they want to be together. Don't put any boundaries between them. Patches that look like they're different stuff, put some boundary in between there. If you see a patch that looks like it's kind of split in half, right? And maybe that tells you there's an edge there with a certain orientation. And if you see a couple of these and they kind of seem to be going like, they seem to like support each other in terms of their continuity, maybe that's important evidence too, right? And like, curves tend to continue, right? When you see boundaries of things like depth boundaries and so on, they have good continuation, right? The world is like pretty structured, or it's not just random particles of noise. All right, so you have all these kind of bottom-up cues, and the whole empire of segmentation algorithms is like trying to mix all these things together in some effective way. Okay, let me pause here 1 second. Well, you'll see my outline in a minute, but the way I made this talk is like I'm just going to blab on for a while, and then there's like hopefully some time at the end where I get some feedback. But you're welcome to just reject that strategy and raise your hand at any time. Okay. So here's the sort of what I think is like high level current context. Okay, so we have seen remarkable progress in the last 10 years and accelerating, it seems, in this ability to train end-to-end systems that seem to do really well at mixing all these cues that I just talked about. And I kind of divide this up into kind of three categories, right? So one category is, I can take images like this. I can get a bunch of humans to label boundaries on there. And maybe they're going to label object boundaries, maybe like material texture boundaries, some weird combination of the two, but I just get a bunch of people to do that. And then I train some kind of network with some parameters theta to try to hit that same thing. So it's just supervised training, right? And my output is a binary map if I get a 1, it's a boundary. If I get a 0, it's not. And with this sort of, and it used to be back in the day that there's this data set of human annotated images, the Berkeley segmentation data set, and we try and get closer and closer to human performance, and if we've like blown that out of the water, right? We saturated that data set. And we always thought, oh, wouldn't it be so cool if we could get there? And now that we're there, we're like, oh, this still kind of sucks. Like, what do we use this for? Okay, another one, and maybe if you saw segment anything in the news, or you played around with it, or you're starting to use it try to use it in your research, is this what I call sort of a conditional mask prediction, right? So somebody gives you like a condition. In this case, the condition is like a query point, like a click somewhere. And what the system does is it basically, predicts a binary mask that says this is the region that contains that pixel. Okay, and the same thing. This is now trained. This now has billions of parameters and has been trained on billions of images, so massive scale, and in kind of an interactive way, where first you bootstrap this thing by training on these things over here, and then you give it to human annotators. They correct it a little bit, and then you refine it, and you keep going like this. And so these are like, if you play around with segment anything, they got a great demo. It's like, at least for someone who's been in the field for a long time, you watch it and you're just like, whoa, that's crazy. It's amazing. And then the last one, which is maybe, intellectually more interesting, is something that's completely unsupervised, right? So basically you take images like this, you put a network on it, like a vision transformer, a VIT model, and you just do something sort of self-supervised where you say, 2 crops of the same image should map to the same thing. And if crops come from different images, they should map to different things. So you just kind of have this contrastive sort of loss. And if you do that with the right architecture, what you find is that like you can feed in an image and it'll learn to just give you a per pixel high dimensional vector. And if you just cluster those vectors, like even just with k-means or something, you get this nice segmentation into objects, object parts, and these are sort of unsupervised kind of semantic features that are just kind of emerging kind of mysteriously, that seem to like really get close to what we want. All right, so that's the context, and it's great. So I have 2 main problems, right? So one problem is like if you go to use this, so here's like a version of segment anything that has some temporal dynamics, so it tries to do tracking. It's like, it's great. You're like, oh, this is awesome. It's awesome. It's awesome. And then all of a sudden it's not awesome. Right. And like, here's 3 sequential frames there. Right. It's predicting a per frame mask, but there's no notion of geometry of this thing, of like curvature or continuity or topology or anything like that. And so the mask is free to change whatever it wants. And so like, like have this video and you're tracking someone else and their head disappears and then it comes back. And it's not clear when that happens what you do. Like, what do I have to fine tune my model? I don't know you're at a loss. And then the other thing is it's sort of got it's really hard to learn and adapt, right? So these things work very well on the images that they've seen, but if you start giving it a new kind of image, then they don't adapt. And so this is like, yeah.
Why would it not have seen this image?
But it maybe it didn't have human annotations on this image. It may have seen this image, but it didn't have the annotations on it.
That would be surprising too, but anyway.
Yeah. So anyway, this is me. So remember what I said with segment anything, right? You can go and give it a prompt. So this is me. This is a video here of me moving my cursor around, and it's sort of predicting different masks as I move my cursor. And sometimes you look at there, see it's getting some illusory contours. But there's no sort of geometrical regularity to this, and it's not even like rotationally equivariant or anything. Like it's and you could say, well, this is like an extreme adaptation. Why should it be able to do that? But it sort of demonstrates this idea that like once you move up too far out of the training set, no matter how big the training set is, if you don't have any notion of geometry, you kind of have trouble learning and adapting. And then there's another one. This is the same. This is like a motion illusion. I don't know if you can see it right there. Oh yeah. So this is a camouflaged version of this famous 2 squares illusion. So this two squares optical flow illusion is fun because, you know, if you play the aperture game and just show someone this aperture, the motion actually looks like it's up and down. Like anyway, if you take a you know, deep optical flow model and you throw it at this image, it does pretty well, but it gives it these kind of weird fuzzy boundaries, which is very different from our perception, right? Our perception is like you just nail these really sharp boundaries, sharp corners. And then the same thing kind of happens in stereo, where, you know, you can show you a random dot stereogram of this kind of shape. And if you were to look at this, like you see a really sharp crease like there, like it's like a really, like you cut your finger on it. And same thing here, you sort of see, just like I showed in the Kanitsa triangle with those illusory contours, you get illusory depth contours. So I show this to your left eye, show this to your right eye, you see this kind of folded piece of paper with these like really sharp discontinuities here. And I brought this just, so this is that old classic stereogram, so I'll kind of pass this around. There's a few different ones in here. Feel free to swap, and you kind of have to move it back and forth to get the effect, but you're welcome to kind of play with that. And those are actually kind of interesting. These silhouette things were created back in the 1920s, but only rediscovered in sort of the psychology vision science literature like around 1998. Okay, so so those are kind of the problems I see with our current approach, and so history suggests maybe there's something else that we could do here, right? So history suggests that maybe there's some benefit to modeling edges and curves and boundaries and that kind of geometry, and so this goes way back to, you know, Canny and Bill Freeman's PhD thesis, where you would have, let's say, like an edge model, and you would try to get sub-pixel localization of that edge model by running a bunch of filters and then analyzing their outputs. And you could say, if I use these filters and I look at these discrete filters and I analyze their outputs, I can actually nail down the precise location of this edge and its orientation and so on. And then there's a work on sort of curve linking, right? So if I have like an edge detector here, it might actually enhance the responses of edge detectors that are out here, because those are kind of, you know, some kind of notion of good continuity. And even the work on like, active contours, where you're trying to minimize, let's say, curvature or length or combinations of those things. And then some work on sort of, you know, graph-based methods of like, if I have these contour segments and I try to solve some graph matching problem to connect them up, maybe I can deal with these kinds of missing pieces and model that geometry. And then some really nice work from Josh Tenenbaum's group on sort of, you know, if you can actually recover this, if you have clean kind of geometric structure, right? This if you have geometric representations under the hood, like a composable causal kind of generative model that you can fit to data like this in an unsupervised way. So what you're seeing in this picture is like, you know, a collection of characters that are in random scripts, and then a generative model for generative models that hypothesizes different kinds of generative models and fits them to the data. And once it's learned that generative model from the data, then it can do things like create new letters that no one's ever seen before. Or if you give it a new script, when you only give it a few examples, it can generalize very, very quickly. And so that kind of geometric composition is sort of something that can be very powerful, right? And so all of this kind of exists, but we haven't really figured out how to realize that promise at scale, right? And so instead, I sort of characterize our current approach with like image generation, diffusion models, any kind of deep model, right? Basically, we're taking an image, and somewhere inside the model, we're forcing it into a representation that looks like this, where we've got heavily strided, large receptive fields, and we're using a feature vector representation at that coarse resolution. And we somehow hope that, you know, somewhere embedded in that set of activations is all the boundary information that we want, but we don't know where it is. And when it goes wrong, we don't know how to fix it, right? And maybe you clean it up with like a conditional random field at the end, but, you know, that's only going to help you in places where there actually is a color difference at the boundary that you're interested in. And so some people might say, hey, we just need bigger video generation models, right? We just need like Sora on steroids. And, another, let's say 2-3 billion, images from now, all this information is going to be, we're just going to be able to pull it out of the activations, and we're not going to have to worry about this geometry. But maybe we're going to run out of computers and power before then. So I'm just kind of working on a plan B. Okay. So the way that I'm going to kind of like structure this proposal, I sort of think of the work that we've been doing as like this, like a process of iterative design, right? So I teach in engineering, and you like teach this notion of iterative design. You like have an idea, you make a prototype, you try it, you get feedback. So that's kind of where we am, and we've been through 2 iterations of design. And basically, we're trying to invent some architecture that might capture these geometry ideas, but be scalable. So that I could just like train a new model with billions of images, and it'll just actually work and be able to consume all that data. So I'm going to present a couple designs, and then hopefully there'll be time at the end where it'll be like a design review. Like, what do you like? What do you don't like? Like, what sucks in my design? What should I fix? All that kind of stuff. Okay, and as you can see, I've been thinking about this for quite a while, and the progress has been slow, so I could use some help. Okay, so at least for me, when I'm doing sort of a iterative design problem, I like to sort of invent some kind of toy problem that I can use to iterate on, and to sort of, some kind of like minimal archetype that captures the essence of the thing that I want to solve, and that I can easily analyze and understand. And so here's this, I call it a toy problem. This is the toy problem. All I want to do is take an image like this that's got simple color-based boundaries of shapes, but it's really noisy. And I want to get back the precise pixel grouping as well as the boundaries. Okay, so that's the and why sort of low SNR? Well, because like if the image is clean, then anything works, right? I can just run k-mean on the pixel colors. I can run a canny edge detector. I can anything you want basically is going to work on this image. But all of these things break down eventually as you increase the degradation level. And if we can find architectures that can endure and succeed despite these sort of high degradations, maybe that's going to be the kind of model that we're after. Okay, so here's an example, right? So here's this is just what happens with existing kind of segmentation grouping methods. So on the left, what I'm showing you is 2 different input images, one that's like perfectly clean, one that's a little noisy. The middle column is like a boundary detector, GPB. It's like, circa 2008, I think. And on the right, you're seeing 2 things. One is a denoising algorithm, L0 smoothing, which basically tries to solve an L0 optimization problem to find the best piecewise constant approximation to your image. And superimposed on that is there's this junction detector, ASJ, which is basically goes around your image and tries to find things that look like junctions. And when it finds them, it sort of spits out the little local junction configuration. And so those things both do, all those 3 algorithms do great. And you add a little bit of noise, and they still do okay, right? GPB breaks down a little bit, the junctions get lost, but the L0 smoothing does pretty well. Okay, now if you keep going, then they really start to fall apart. And if you like, you can do things like, well, maybe I can run a denoiser and then run those algorithms. And even if you do that, once you get down to serious levels of noise, right, everything falls apart. Yeah.
But you mentioned in the previous, like in the short problem definition, that if you've got an image that has no noise in it, that anything works.
Right.
So doesn't that mean that ultimately it can become a denoising problem? I mean, maybe these denoisers are not good enough, but that effectively it's a denoising problem?
Well, so if what you want is a pixel perfect estimate of your signal, then I think of that as like you want to get all the texture details and all the, like if I wanted, let's say like in a low light imaging scenario, I have a single shot, it's noisy, and I want something that's photographically appealing, then yeah, I agree that's a denoising problem. And I think, but if what I want is kind of a cartoon of my image, right? So I don't want photographic quality. What I know is where the boundaries are, right? What the material properties are in those segments. It's like a spatial cartoon, but with precise boundaries. And so what I'm looking for is not something that gives me a perfectly denoised version of the image, but something that gives me stable structure the structure is resilient to these kinds of degradations.
I mean, I totally understand your goals. It's just that the setup of the toy problem, I think, may conflate.
Yes, fair enough. Fair enough. Yeah, and I guess to just call it I guess maybe the sort of low SNR is kind of vague because I could apply various kinds of degradations, right? Motion blur, defocus blur, like kind of whatever I wanted. No, but I agree. That's good. That's exactly. That's actually much preferred. So please jump in. Okay, and then yeah, you can do other things like these sort of deep learn methods and so on, and they all kind of fall apart. Okay. Okay, so this is the toy problem. So now we need some kind of design goals, right? It's so here are my basically 4 design goals. So number 1, so anytime you have this kind of problem, you need some regularizer. Sort of your sort of your prior on what kind of shapes of curves and boundaries you want to see. And basically, I want something that like prefers low curvature kind of pieces, but also allows, like if you think of a boundary curve as some one-dimensional kind of manifold-like structure on your image, I want it contains sort of zero-dimensional discontinuity events, like corners, where there's an orientation change, or like a junction, right? Things where those are really singularities in the boundary set. And I want my regularizer to preserve those things, and localize them. So that's one. So the other is I wanted to exploit all the kind of boundary cues simultaneously. So all the things that I mentioned before. So like, regions that look the same should be together. Regions that look different should look different. If you have regions that look like they're kind of split halves, they should align. And if you have regions that look like they're sort of more split into like, more angular wedges, all those things should sort of align with each other. And so what that'll mean is that, when I get my boundaries out, not will I just have this boundary set, but I'll actually have like some structure to it. I'll know where the corners and junctions are and what their angles are and so like. And then the other thing is, like I said, I want this to scale, right? So I don't want this to be some hokey, like, house of cards. I apply this step, this step, this step, this step. And I wanted the whole thing to be differentiable so I can learn it end to end. It can suck in data, and it can actually work for most of the time, all the time. And then the other one is I'm thinking of this as like a bot, like there can be like the kind of top-down stuff I was telling you about, like semantic language models and like clip embeddings and like dyno features and stable diffusion features. Like, great. Those people are giving me all the top-down stuff I need. What I need is a little bottom-up cleaner and tightener. And so I want my processor to be shift invariant, right? So everything's going to operate on sort of small receptive fields, and I should be able to train this on small images and deploy it at arbitrary resolutions. I should be able to, if I have a big image, I should be able to chop it up into patches, or tiles, and analyze each tile independently and put them back together, and all that should work. Okay, so the representation that I'm proposing, this is the only thing I could think of. It's like the limits of my imagination, is to represent the image as a field of, okay, I'll skip this part, as a field of local shapes. Okay, so here's the idea. Your input coming in as an image, this thing on this left, and now I'm going to get a little persnickety about when things are discrete, like pixel values in an image, and when things are continuous. So I'm drawing these little blue dots here to represent pixel samples. And this is so I get a value at every vector at every pixel. So imagine this could be RGB. I get a 3 vector at every pixel, but like you could apply what I'm going to talk about to be any k-dimensional feature that you have here. That's my input. And my output is at every pixel, a set of numbers. Just ignore all this sort of mathy stuff right here. It's a set of numbers. In particular, it's like 6 numbers that specify at that pixel what's the little local shape of the region around that pixel. Okay. And think of this as like a little vector graphics primitive that is sort of describing this local shape in an unrasterized way. And the particular shape space that we've happened upon, and this was Dora's idea, it seems to be working well for us, so we're sticking with it, is to represent this region here using this set of numbers. And basically, you sort of imagine that there's a vertex here that can move around. And there's an orientation that just rotates this whole thing around the vertex. And then there's three angles that basically subdivide it into three wedges, angular wedges that sum to 2 pi. Okay, so you can think of that as like you have a vertex, you get an orientation, and then these three numbers you can sort of think as like a point on the 2 simplex, right? Because they sort of have a fixed sum. All right, and you can generalize this to more angular wedges like 4 or 5, or go down to 2 if you want, whatever. Okay, so why I like this space is because A, it's nice. It's a nice smooth space. You can just interpolate in this space, and it's kind of continuously defined. And B, it's like very inclusive, right? So I can take this vertex and I can move it outside of the patch, and I can get patches that are completely uniform, or that look like an edge, or that look like a bar, or a wedge, or a corner. I can sort of like I get the whole sort of inclusive space of local shapes. And so there's some links here where you can go around and play around with these shapes. So like here's an example right here. You can sort of like drag this around. You can just move around continuously. And with each one of these shapes, you also have sort of an analytic expression for the unsigned distance map for the boundaries that come with that. So all of this is kind of analytic and unrasterized. Okay. And so that's it. Your input's an image, your output is this field. And it's a little hard to visualize this field, right? Because you sort of take this image, I could blow up all the stride 1 patches, right? So these are all overlapping patches. And for every one of those patches, I've got a little estimate of what its little junction shape is at that. And that's it. That's the input, that's the output. Yeah.
The size of the region fixed.
So in design iteration 1, the size is fixed. So you pre-choose a scale. And design iteration 2, we relax. We let it adapt spatially.
The other question I had was when the vertex is outside the region, there's some ambiguity, right? Could be many different parameters that give you the exact same shape.
You give me the exact same kind of like boundary pattern, local boundary pattern. So the way that could be design iteration 3, but the way we're approaching this right now is no, it doesn't matter. And moreover, there's some permutation ambiguity, right? You can imagine like swapping 1, 2, 3. I could make it 2, 3, like, right? And you see that here, right? So you see that happening right here. Like in this case, these are 2 overlapping patches. They've both got the same boundary structure, but in this case, there's been a labeling permutation. And right now, we don't try to resolve that. We basically, what I'm going to show you is we basically just find different ways of succeeding in spite of that. But there's definitely, that's something to think about. Okay, so that's the input, that's the output. Now, what do you do with this output? So to kind of relate this, well, A, how do you estimate it? We'll get to that. But B, what do you do with this field? So to link it back to the image, I got to kind of introduce a couple operators. So one operator, I'm going to call it like a gather operator. All right. So imagine you take one of these patches and you go back to the original image, and you have sort of a little gathering operation where within each wedge, you just take an average of the image colors in those 3 regions, right? So this little junction is okay, and if you do that in every patch, you get something like this. Okay, so I'm going to call that a little gather. And then a slice operation says, now that I have these, if I look at a certain pixel, there's a whole bunch of patches that overlap that pixel, and they're all making a different prediction for that pixel's color. So I'm just going to average all those together. Okay, and I'm going to sort of slice through the patches. And if you do that, then you get this. Okay, so that's like so I've kind of like gone from the field to this kind of like boundary aware smoothing based on that field. The other thing is, right, each one of these patches also, like I said, has this associated unsigned distance function. So again, I can just like slice through those, basically put them all on top of each other, average pixel-wise, and I get kind of a global distance map to the boundaries. And then I can just apply a nonlinearity to that, right, to sort of capture the zero level set, and I can sort of get the boundaries out of that. Okay. And so I'm going to sort of call these like, these are just like, my output is this field, and it kind of implies all these kind of global maps, but the field itself is the thing that really is what's being estimated. And I left a little spot here because there's a fourth one, which is a little bit harder to understand. But so imagine thinking about this pixel right here, and thinking of all of the little wedges that cover that pixel, right? So it's covered by this blue wedge and this blue wedge and this blue wedge. And so imagine taking all of the wedges and adding them up, and then normalizing it so it sums to one. It would be like a little affinity map. Like, how much does this pixel like all the other pixels around it? And so that gives you this kind of like this kind of affinity map where I can like, I can scroll around here. Maybe this will work. So I can scroll around here, right? And I get these like little affinities of like how much every pixel likes every other pixel. And in fact, this sort of this smooth color that I was telling you about here is really just using these as a spatial averaging kernel and applying it to the input image. Okay. Good. So all of those things relate the field back to the image. And then here's some other things that we've thought of how you could use this kind of field if you could successfully infer it, right? Because it gives you the lines, the curves, the corners, the junctions. You can also figure out places where you have vertices that like really cluster together, because that means there's like a corner or a junction, and then you can estimate the orientation there. So you can use these as like affine invariant interest points, and actually they could be even like quasi-projective invariant interest points. You can use this kind of for stylization, because you can, not that we need another stylization algorithm. And then the other thing is that, I kind of describe these output maps as sort of discrete things, but they're not. They're actually continuous things, right? Because this field here is specifying the location of everything in a continuous, unrasterized sense. So I can apply, I can apply transforms. I can scale this thing. I can stretch them. And so you get this kind of like, potential for like scale invariance. So if you had like a robot going around and it needed like a stable zoom invariant representation of structure in the world, this could be something that could be useful in that context. Okay, so now that the real question is, how do you go from here to here? Okay, so this is sort of the first design. This is Doerr's creation. So he basically did this without any learning. It was like good engineering and clever optimization. And so the first thing he did is said, what if I just want to fit a single junction into a small patch, right? So you basically have to search over this space of vertex, angles, orientation, and every time you find one, you use it to average out the colors in the three wedges, and then you compare how close is it to the actual image, right? So it's like the optimal sort of piecewise constant color fit to my patch with this constrained parametric geometry model. And how can I do this in a way that like survives even when the noise gets really high? And so this is basically he spent a long time trying to solve this with learning and all kinds of things. The best he could come up with is like some kind of specialized coordinate descent. And this is what the loss landscape looks like. It's pretty nasty. Okay, but the next thing is, so let's suppose I take an image and I do this independently for every patch. Most of the time it's going to be good. Sometimes it's going to be bad. So now basically you want to optimize this where you have kind of like an MRF kind of like optimizer where you say every patch has to like its local data in this sense, and then they also have to agree spatial, like consistency wise. And consistency is just really simple. All I just say is that at every pixel I can look at the distance, unsigned distance predicted from all the patches above it, and that has to be low variance, right? Which is basically like saying you've got sort of pairwise connections between patches over some kind of Markov blanket. Okay, so anyway, Dora wrote some really nice code for this. It's like 150 lines of Python code. It's really efficient. It's not fast, but it works really well. And it's only got 2 parameters. And this will come back to what Kiros was asking, right? You have to choose the patch size, and you have this consistency weight. And here's kind of how it behaves. And I was going to try to describe this, but Dora actually just describes it really well in a video he made, so I'll let him play it.
Curve contour is a collection of shifting corners. By increasing the boundary consistency weight, so the corners is heavily penalized, causing our corners to shift toward each other.
All right, so got it? Got it now? Oh yeah. Okay. So this is what consistency does, right? If you relax it, you can represent curved pieces okay. And if you really tighten it up, you get little polygons because everything wants to slide and really agree with each other. And then the scale parameter kind of has this effect, right? So this is in the high consistency regime, right? As you increase the patch size, basically it says in every patch, you've got to have something that looks like one of these junctions. And so your polygons become further and further and further apart. And basically the patch size is like a lower limit on how close 2 vertices can be, 2 junctions or corners can be to each other. All right. So one thing I just want to point out, if you're like into the kind of image processing, signal processing kind of world, is like this ability to regularize to piecewise low curvature segments while preserving discontinuities in orientation or curvature really doesn't exist. Like there's no other way to do this, right? So the closest thing you could find in the image processing world is like, this is like a Elastica-Chan-Vezé kind of variational regularizer with level sets, where basically you're saying, I want to find a curve that has some either smallest length or smallest curvature that explains my image. And like you always get rounded corners and you can never represent junctions. And this would be true if you like tried to fit a neural field to represent this signal, right? You're never going to be able to get something that has these kinds of discontinuities in it. So there's really no alternatives here. Okay, so the other point is that both the initialization and the refinement matter, right? So if you have something that's clean, you can just run the initialization, that's great. But as things get noisy, then you get this sort of thing, and then after you run refinement, it kind of cleans it up. And then, there's like Dora really went to town. There's like a 20-page supplement in this where I explored all kinds of variations of this, right? So you can use 4 junctions instead of 3 junctions, and then you can capture X junctions. On the gather step, instead of saying that things have to be constant in every wedge, you can say that it's linear or quadratic. There's no real extra computational burden to doing that, so you can get better representations that way. And of course, like the number of channels is kind of arbitrary. So if you had RGBD or like any other kind of vector input, you could just play the same game. Okay, I'm going to skip those. Okay, so now design 2. Well, there's basically 2 things wrong with design 1. Number 1, we had to pick the patch size ahead of time. And it's got to be the same everywhere. And number 2, it's not fast. It's not feed forward. It's not differentiable. It doesn't scale. So we want to fix that. Okay, so the first thing we want to do is fix the patch size. So far, everything that I've talked about has been sort of geometry and optimization and mathematics. Here we kind of transition to like the learning part of the talk where it becomes a little less formal and a little more kind of trial and error. And as you probably all know, there's lots of trial and error that went into this, and I'm just going to give you the stuff that actually works. And if you want to ask all the gory details of what didn't work, I can tell you all about that some other time. Okay, so what we want to do is basically add to each one of these little patches here kind of a windowing function that says, like trust this part of the window, but not this part of the window. And the representation that we found to be the best for this, with the architecture that we ended up with, is this kind of convex composition of bases. So basically, the windowing function is just a convex combination of these three kind of pillboxes, and you infer that at every patch. And so this would effectively be a very small patch size, and this one is a much bigger patch size. And so it's not a great family of windowing functions, but it's the thing that we found so far that works best. And so, what's that? It's no, they sum to one. They sum to one. Yeah. So it's like, yeah, it's a point on the two simplex. Okay, so that just improves the quality of the implied global maps, because now when you do this kind of gathering and slicing, you use these windowing functions, and now you can have places where you have lots of little fine scale geometry and places where you have bigger scale geometry. And now what we want to do is basically have some kind of feed forward architecture that takes an image in, gives me an initial estimate of these two fields, and then refines them over time, right? In the spirit of what Dor designed, but in a way that can be learned and accelerated and scaled. And this is, if anyone's familiar with like Raft optical flow or Raft stereo, this has that kind of flavor, right? Where you fix the number of iterations and you just train the whole thing end to end. And I'm not going to go through all the details of all the little pieces of this, but here's the high level structure of the whole engine, right? So the first thing to notice, right, there's basically these three kind of blocks in here. All these things are shift invariant, so they all operate on little small patches. And so basically there's a little feed forward network here. We found an MLP mixer to be the right thing, at least the best we could find. It takes a little window of pixels and spits out a high dimensional vector, like a d-dimensional vector, that we hope encodes kind of the junction information and the patch size information in that little region. Okay, so this think of this as like the initialization in this sort of abstract embedding space. And then we have several iterations just of self-attention, where each one of these hidden states sort of looks at its neighbors. It's kind of like each junction looking at its little junctions around it and saying, yeah, how should I change myself? Right? It looks like there's a line over here, maybe I should move over here. And that's what these iterations are. We run like 7 iterations of these. It's kind of like a little, and there's like other transformery things in there, like normalizations and MLPs and so on, but that's the rough idea. And then at the end, when this comes out, now you've got a d-dimensional vector at every pixel, and now you've got to map that just with an MLP down to this junction and patch space. Okay. So this whole thing is like shift invariant. And, after many sort of trial and error, Mia was able to pare this down to a very small number of parameters. And it's pretty fast, way faster than the design one. And it scales way more. And we train it just with like the simplest things that we could imagine, right? So we just make these images with circles and triangles. We like circles and triangles. Because they give you all kinds of corners and junctions and so on, and because for each configuration of circles and triangles, we actually have analytic expressions for these unrasterized, unsigned distance maps. And then the losses are really simple. Like you basically got to get distance field that match these ones, and we found it's useful to have this sort of self-consistency where the sort of pixel-wise variance of the overlapping patches is small. Okay, and so once you train this thing, you can try to probe it and say, like, is it doing something reasonable? And so one thing you can do is like this little MLP here that sort of examines this latent high dimensional sort of hidden state and decodes it into a junction, right? I can apply that probe at various points in the infrastructure, in the architecture, to see what it's getting, and we find that it sort of has sort of this like earlier kind of exploration phase, and then things kind of tend to tighten up as you go on in iterations. And then the other thing that you could do is you could say, well, does this hidden latent space, right, this high dimensional embedding of these little junction geometries, does it actually have any kind of nice properties? Like, is it smooth, for example, or is it just kind of random? So you can play the following game, right? I can basically take two hidden states, and I can map them to their corresponding junctions. That's what these are. And I can see if I just put all zeros there and pass it into my MLP, what does it give me? Turns out it gives me this. And then I can just do linear interpolation in this d-dimensional space, and for each time I can map it down to see what junction it's representing, and we do see that it has this nice sort of continuity in it. And for comparison, I can do the same thing like in math, right? So each one of these, like I can define my canonical junction as a vertex in the middle, zero orientation, and equal angles. And I know the junction parameters here, and I can interpolate in this space. So I just linearly interpolate in R2. I do circular interpolation in S1. I do geodesic interpolation on the 2 simplex, and you sort of see something that's kind of very similar, right? Okay, and you know, then you can go and apply this to actual images and sort of see what it does. Yeah.
Well, if that's the case, do you really need to learn it? I mean, if your latent space is
no, because so you need to learn something, because remember I said the initialization, right? The initialization to get Doer's algorithm to work, you had to have a really good initialization with this really complicated coordinate descent, and this is gone here. Here, like the initialization is bad. It's like a little feed forward network, right? And so in order to be able to clean that up, you've got to be able to use sort of non-local signals. Like I got to be able to see, oh yeah, there's kind of like an edge coming down here. Maybe I should have a junction here. So you need to sort of have some like notion of like what is it? How consistent is this sort of junction configuration here with this junction configuration here?
I guess you will need to do some learning, but the question is the latent space kind of known what that is?
Is it what?
No, essentially, at least you have some idea.
Well, I need it to be, yeah, I guess you could try to learn it otherwise. I guess, so I think what the reason why we ended up here is because this dot product self-attention is a very flexible way to encode sort of notions of geometric consistency, right? Like it's like basically this junction is looking at all of the junctions around it and saying, how should I evolve? And I think that it would be very hard to invent a mathematical scheme that operates in this lower dimensional space that has the same kind of expressibility and trainability. Okay, and then, you know, so with, like to sort of, you know, I always have to like suggest, like need some kind of application. So you can apply this to like low light imaging or something where you're trying to recover stable structure despite increasing sort of photographic sensor noise. And so you can sort of compare and show that it does, you know, has more stability in these kinds of things, and it's much faster than design one, and so on. So that's it. And I'm realizing this talk is structured in a very kind of anticlimactic way. Like you're waiting for like some punchline, like, oh, now your representation like solved all my problems. So I apologize for the letdown. What I sort of hope to gain from this interaction, and hope that you might gain from this interaction, is really, you know, going back to this kind of idea, right? That if we can find representations that that allow us to sort of move beyond this activation soup and actually have some geometry baked into them, right? Maybe I don't have to increase the dimensionality of the features inside my model, but I just need to structure them and disentangle them in a certain way. Then we can both do sort of, you know, we can both do more efficient learning, but we can do more efficient adaptation as well. And I'm hoping that, you know, maybe even if you don't remember or care about anything that I talked about, if you start thinking about, how could I sort of, or if you find yourself in a place where your boundaries are just not where you want them to be, to maybe start thinking about these kinds of things, and we can work together to make progress. Okay, so I think I maybe used too much time to allow for design review, but that was sort of meant to be the context of this, is like along the lines of Kiros here, like, what don't you like about, how did I offend you, basically? And what would you like to see in like version 3? Or what do you think is missing from this whole thing, or what's misguided about it?
We can still clap, right?
Okay, now end.
Maybe can I ask a question and stuff? One thing that's pretty remarkable is that the training for this is just the circles and triangles. Is that right? And then you apply it off the shelf to all these other sorts of images, and it just works?
Yeah, I mean, it works, but I guess there's a question of like, it works for what, right? So I think like what I want to do with this is now, like, take this kind of architecture, and instead of feeding in RGB, I can feed in optical flow and monocular depth and dyno features and SD features, right? And when I do these kinds of gathering, like this gather operation that I'm doing in every wedge, right now we're just averaging, but that could be like a slot attention-y kind of cluster, right? And then I should have a code book here where I have a certain number of slots per image. And then the output, should be like, can I do accurate temporal prediction in a video? Like I sort of feel like this is just a step towards what we really want, is unsupervised learning of vision and perceptual grouping from unsupervised video, right? So I think, so yeah, it does these things just from these little circles and triangles, but the things that it does right now are not, as you saw by the end of the talk, right? Like I feel like we gotta put it inside other things to actually see where it's going to shine. But I guess the reason I think you're right, that like the fact that it does generalize from such simple things to less simple things gives me hope that now it's like, when we add all these other stuff on top of it, that it's actually going to, help out there as well.
Thank you very much for the presentation, and it was a pleasure reading the paper. I'm not very surprised that you settled for attention model. In a previous work, you showed that attention in transformers actually do perceptual grouping, which is somewhat what you are trying to do, to assign labels while you keep the local sensitivity. I have two questions for you. One is, how robust is the second design to zoom out for representing curved segments that are really curved? And the other question is, you mentioned interest in biological vision. My question is, how do you see this work can be extended to represent more mid-level, high-level representations from the visual cortex, mainly convexity and concavity? That sort of requires like global contact, not just local.
Yeah. So great. So I would love to know more about your analysis of transformer work. So maybe afterwards, if you could talk to me, that'd be great. Okay. So in terms of perceptual grouping, right? So once you have this field, maybe I have this. I think this is the picture that. So once you have this field, right? What we're not doing right now is assigning a relative depth ordering to these layers, right? So another thing that you would like to do is, if I break up a region into two segments, or 3 segments, I want a depth ordering, which one's in front of the other. And I think there's a lot of, and I have one student who's playing around with this now, right? So in the perceptual grouping literature, like the way that we do sort of figure ground assignments, right? We have like a convexity prior, right? So if you see a convex boundary, you sort of see one side as being in front of the other. And when you see a T-junction, right, typically it means that this thing's in front of something else. And so I think this kind of structure can actually, if we augment the model to include layering, might give us a way to sort of do things like not just illusory contours, but amodal completion and all that kind of stuff. And then in terms of the high level, like coming back to the Knizia triangle, like, well, how do we get it to work on the Knizia triangle, right? You need something that likes triangles more than Pac-Man, right? Or that says, three Pac-Man at these weird orientations is just not really likely, so I'm going to pick the triangle explanation. And really, I think of like, this is a bottom-up model. Where does the top-down come in? And I don't know. I got two ideas here. One is I have sort of features like so these semantic features I was talking about, like Dino VIT features or stable diffusion features, where you put in an image and you get a high dimensional vector at every pixel that basically encodes the semantics of that pixel. And so you could plug that in as input. So now, in addition to all of the local RGB, you actually have a vector that says, this is what you are. You're a horse or whatever. You're the leg of a horse, in fact. You're a leg of a horse in a green field with the sky above you. All of that information is right there. So that's the dumb way, right? Like I don't have to try any new architecture. I just take my existing architecture and apply it to different input. The smarter way would be to like, how do we actually do the global processing at the same time or in some co-evolution way? And one simple idea, and this is that, see, if you think of these affinities right here, you can actually build an affinity matrix, right? So I can build a big pixel by pixel affinity matrix, and then I can do spectral embedding on that matrix. And when you do that, right, these are like the first 6 eigenvectors of spectral embedding. So there is, right, and so like somehow, and I could now I've got a new 6-dimensional vector at every point, and the variations within these segments is now linear. And so somehow, like, I don't know, maybe there's like some global eigenvector analysis that is like happening in conjunction with this, that is somehow taking this local grouping and globalizing it, and then bringing back in a way where it can feed into the next iteration of self-attention. So, I mean, these are all sort of vague and fuzzy, but I think those are really interesting questions.
Right now, your design is like you're assuming that the outputs, the boundary, the embeddings that you have are like kind of unimodal given the patches, the degraded patches, and what do you think about like that assumption?
Yeah, no, I don't like that either. So actually, that's what Mia's working on right now, is like, just instead of thinking this in a raft-like framework where you just fix the number of iterations and you just have a point estimate at the end and you try to optimize the accuracy of that point estimate, just think of this as your UNet in a diffusion model. And you go from random noise to a distribution of boundaries at the output. And I think that's just like, if we started the project again, we'd do that first, but time moves a little faster than that these days. But I think, yeah, that's like ideally for the Knizia triangle, I'd like to see a distribution of groupings. Sometimes the Pac-Man, sometimes the triangle, right? Something like, and that I'm all into this like distributional notion of perception.
Maybe we take one more question, if there's one.
Just one quick question. So on the previous work before the deep learning version, so I really like the idea here that you said you can go beyond RGB. It can be, it's just k-dimensional, but if you don't mind going back just so I understand, that first one that you did, I guess the CBPR 21.
Yep.
The optimization function, that convex space is for RGB. I mean, this would be more complicated if you started tagging K on there.
Not at all.
Is it the same here? This could be.
Yeah, absolutely. Yeah, no, absolutely. You could do it.
Those experiences, you're pretty thorough
Yeah.
on your experience. But I really liked it because now you can start mixing and matching and you just run, you can take and run a bunch of off the shelf, whatever. Like you said, it's exactly what we do teach. Here's in segmentation algorithm, take your favorite, whatever word. But I like the idea that you can take the whole bunch, just have a big dimensional vector and say, okay, now go apply this here. Right?
Yeah. No, I agree. We've gone to 4 channels from 3 to 4 RGBD, right? That's kind of as far as we've gone.
David, I know you said one question. It's a multi-question. Sorry.
Multi-part?
This slide, there's one more question I did have, especially your toy example. Maybe you go back to the toy example where you just said, hey, I want to be able to handle this in different ways.
Yeah.
It does, I think all of us older folks who've been working longer, like this particular example, it does kind of start to raise the question of like scale space in the sense that, at a certain level, maybe I want all those little noise thing boundaries, right? I think one thing that's really surprising is you run candy detection, it's great. And then you give me a 48 megapixel image, and I run candy detection, and I get all the noise out. Right? So you also have, I know you kind of use fixed windows when you went to a set of fixed windows, but you're still aperturing the top. Right? And so at some point, there must be a decision on, okay, what, you have to define it, right? This is the scale space I'm going to work on, this is the aperture I'm going to have. That's just kind of inherently built into your system based on the fact that it's window based.
Yeah.
And I really like your approach. I think any student watching, I like this idea of take a toy problem and see if you can solve that first before you download a million images and hire 1,000 people to make it. But you do have to define there's a certain, I have to make some assumptions.
Yeah.
I think this one, there is a notion of it. And at some point, the noise got so much, I couldn't see what it was. Okay, I can't tell. Maybe maybe the noise introduced another structure inside there at some point. It's so corrupted. So right now your scale is basically, this notion of scale is limited to the window size.
Absolutely. And in the second part, even in the learning-based version, right, there's a maximum window size, and then we kind of have a windowing function in that.
Exactly.
And there was a question about like how stable is it over sort of zoom levels? Well, that limits it, right? Because like if you want to go from really small patches to really big patches, then you need to have all of those different patch sizes in your catalog. And right now we don't, just felt like we ran out of memory and so on. And I think this also relates to the sort of the distributional suggestion, right? Is I don't just want to pick it, like whether you want the fine scale detail or the coarse geometry depends on your task. And so really you want a sort of a distribution of all of these things, and then you're downstream, you can pick the ones I think that you need for whatever you want to do.
Or was there another part?
No, that was it. Sorry.
Okay.
I do the one.
All right.
So this is fantastic. I love it. My question was about the fact that this representation seems to give very special sort of attention to images, 2D images. And when you go to video where you have like another temporal dimension, or when you're dealing with 3D data, which have their own structures, how easy is it to generalize this notion of a junction to higher dimensions? Because it would seem to me that it becomes a bit messy.
I'm laughing because I literally spent the last 3 weeks in like slightly visualizing these 3D junctions, and I like rip my hair, like I give up and I'm frustrated. I storm away, and then 2 days later I come back and I try again. I don't know. Basically in 3D, I've been trying to invent just breaking. So think of like the sphere of directions around a vertex, breaking it up into 2 pieces with kind of planar facets. Right. So that seems like, okay, if I just do that, and I'm trying to invent a smooth representation of that, I haven't succeeded. And that's just that little special problem. I think it's possible, but it does get ugly. So another option is to play the game where you have these regularizers operating on the images, and you're inferring a 3D latent structure that when projected has this two-dimensional regularity, right? It's kind of the game we play with like a lot of 3D stuff right now. So that's the sort of the maybe more learning, like less fun math version. So, but I'll leave that to someone else.